Yo, what's up, Sci-Fam? Here we are, Absolute Age Dating, Part 2, where we're going to look at types of radiometric dating, including looking at igneous rocks, zircon crystals, carbon dating, and also we'll understand what index fossils are by the end. So let's get started. This is page 2 for the Absolute Age Dating, and we're looking at types of radiometric dating. Remember, radiometric dating uses radioactive decay to understand how isotopes change into their daughter elements. The first thing we can look at are igneous rocks. And igneous rocks are important here because igneous rocks are molten rock that is also known as magma. And when that magma cools, it also crystallizes. So it cools and crystallizes, which means that it then hardens in that moment. It was a magma, ooey gooey rock. When it crystallizes then, the elements that are in there, it basically starts that half-life clock at 0. And it contains, igneous rocks at least, contain radioactive elements. Now what's interesting is that sedimentary rock also contains radioactive elements, but sedimentary rock is basically a bunch of igneous rocks and other stuff that breaks down over time. So if you were to take a radioactive sample of sedimentary rocks, when that sedimentary rock formed, it actually already had igneous rock in it as part of it, and that igneous rock formed way before the sedimentary rock formed. The sedimentary rock is just made up of a bunch of little tiny parts and pieces of other rocks. So you can't take a sample of a sedimentary rock because this intrusion, this thing in the sedimentary layer, might have a different layer than a piece right next to it, which might have a different layer than a piece right next to it because each of those came from a different larger rock. They got weathered down or destroyed to become a smaller piece, which made that sedimentary rock. So igneous rocks, which are just the rocks that are cooled magma that crystallize, since they contain radioactive elements, and it all happens at once when igneous rock layer forms, then the radioactive elements start decaying at that moment at time 0, and so it continues from there. So we can use the igneous rock layers. Now those radioactive elements, some of them that are famous, first off we have uranium, the most famous of them all. And that on the periodic table is just the letter U with a box around it to give us that understanding that that's the chemical notation, the scientific notation for uranium. Another famous one that is in igneous rock is potassium. And potassium can also be found in bananas, but on the periodic table it's noted with the letter K. And lastly we have rubidium. And rubidium on the periodic table of elements is Rb. So use that box to signify that we're looking at elements on the periodic table of elements. Now, these are all radioactive elements, so as a parent element, these are each parent elements, and they'll decay into daughter elements. So since they decay, we would say that these are radioactive. They're active, meaning that they will decay. And when they decay into a more stable form. And so we call that the stable daughter. The radioactive parent decays into more stable form called the daughter, or the daughter isotope. So let's put some examples in here, and let's actually look at the actual amount of time that it takes for some of these radioactive elements to go through one of their half-lives. So let's say we start with potassium 40 as the isotope, meaning it has 40 neutrons in its nucleus. It is going to decay over time into argon 40 because this is the isotope of argon it will break down into, and this process would take, for half of it to break down into argon 40, it would take 1.25 billion years. Whoa. All right, what about rubidium? Let's take a look at rubidium 87. Rubidium 87 will break down and become a more stable strontium 87. This process takes 48.8 billion years for half of it to break down into strontium. That takes a long time. Next, let's take a look at some uranium isotopes. So first, let's look at uranium-235. We'll look at two of the most popular ones. So uranium-235 would decay into lead 207. In lead 207, when you have half of the sample of uranium-235 that is now turned into the daughter form of lead-207, this process for half of it would take 704 million years. What about one that's a little different, uranium-238? This is going to decay into lead-206, and this would take, for half of it to decay into lead-206, would take 4.47 billion years. So you can imagine that if we know that half of a sample of rock, let's say this is my rock here, if we know that half of the sample, and obviously it wouldn't be just this one half, but if we looked at all the atoms in my rock sample, if half of them had gone from uranium-238 to, let's say, lead-206, if half of it happened, then I would know that that rock is 4.47 billion years old. If I had potassium-40, I had a sample of potassium-40, and half of it was now argon-40 when I looked at the sample, then I would know that 1.25 billion years had taken place. So you can see how knowing what the parent radioactive isotope is and knowing what it will decay into, we can look at the ratio of parent to daughter to figure out if it's 50-50, we know one half-life has happened. And if it's a different ratio, then we can use some math to figure out how many years has passed. So that's looking at igneous rocks. Now there's another type of thing that's like a rock, but it's actually just a single crystal, meaning that it's just made out of zircon. So if we have a zircon crystal, these are very small crystals, and they're nearly indestructible. Now this is a good trait because it means that they don't get crushed very easily or broken down very easily. So the fact that they're indestructible means that they'll stay around for a long time. Now these zircon crystals contain uranium in them, which is one of those radioactive elements. Uranium. So they're nearly indestructible. They contain uranium, but they cannot form when the lead is present in the magma. Now, think about this for a second. The reason that this matters is because if zircon crystals are made out of uranium and they can't form when lead is around, then we know very precisely about the time period in which the zircon crystal was created, because if uranium breaks down into lead, we know that every single piece of lead in that zircon crystal, if we find lead in it, had to have happened since day one, because that crystal would have never even formed if some lead was there. So if there's now lead in it, it means it only happened through the process of radioactive decay. So that's pretty cool. We can use those zircon crystals, which are found actually in the Jack Hills of Australia. Let's take a look at the satellite imagery of Jack Hills. There we are in Australia. And if we go ahead and zoom in here to the Jack Hills area, you can see some of those pictures on the left. What's fascinating here is that even the satellite imagery actually shows that blue type of hue. And I'm guessing, I've never been there, but I'm guessing that maybe, probably, that has something to do with these crystals. It looks like about the same color there. All right, let's move on to another type of absolute age dating. Type 3 that we're going to look at today is carbon dating. So if you've ever heard, we are a carbon life form. Anything that's alive uses carbon. So this one's a little bit different because carbon can be used to date any biotic, meaning anything that was once living. So it can be used to date biotic things, which is super cool because when we find old fragments from bones, those were once living, we can use carbon dating. If we find some hair, for example, in a tomb, we can use carbon dating to figure out when that person was buried, how long they've been buried for. So the example then that we'll use is carbon. Well, carbon as a parent isotope, we're going to say is going to be C14, carbon 14, and that turns into nitrogen 14. So it's just like those radioactive elements we looked at before. However, now when we look at carbon, Carbon, one of the isotopes, is 14, meaning it has 14 neutrons in the nucleus. When the nucleus decays, it becomes nitrogen 14. This process is a lot shorter than some of those other elements we were looking at. This takes just 5,730 years. Now what this means then is that if we have a sample, let's say this is a piece of hair, we look at the piece of hair and half of it has turned into nitrogen 14, half of it's still carbon 14. Well, that one half-life, meaning that half of it is the new daughter element, took 5,730 years. So you can say, let's say that's about 6,000 years for that to happen. For this next half, it would take another 6,000 years. So let's see, we have 6,000 plus 6,000. So right now, 12,000 years for this much of the sample to turn into nitrogen 14. Another 6,000, so now we're at 18,000 years. Another 6,000 here. 24,000 years. Another 6,000 here, 30,000 years, and so on. So you can imagine at some point there's not going to be much carbon 14 left, which means we can no longer see how long it's been, because if it's all nitrogen 14, then we've overextended our clock. So then what that means then is that carbon dating is only useful for items that are going to be less than about 50,000 years old. So they have to be from now until 50,000 years ago. If it's beyond that and it was living, we can't use carbon dating, simply because of the way that isotope breaks down into nitrogen 14 so fast. We missed the clock. So there is one other form of absolute dating, and it doesn't relate to the way that isotopes break down. Instead, these things are known as index fossils. Now, there are things that were living much before 50,000 years ago. And so some of these things have been fossilized. And the example we'll look at here is something that's known as a paradoxide trilobite. These were only found from about 540 to 485 million years ago. So anytime we would find one of these fossils here in a rock layer, we can then deduce that this rock layer is going to be something between 540 to 485 million years ago is when this formed, because, well, it's got that fossil within it. You can see that fossil over here as well. There's another example of that fossil. So in order for something to be considered an index fossil, it is going to be a fossil that must be very, 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 very common. So common that it's actually found, or could be found, all across the world, all around the world, in layers on all areas of the globe, found all around the world. And it must have lived and died within a narrow time period. Because if they've been around even still today, then, well, if it's here today and we find it in the rock layer, we can't prove that that rock's super, super, super old, because it could have died yesterday and fossilized. Well, fossilization doesn't take that, or it takes much longer than that, but you get my point here. So it's an index fossil is a fossil that must be very common, found all around the world, lived and died in a narrow period of time, or we'll say lived and died in a narrow time period. An example of that is then that paradoxide trilobite. Paradoxidae, maybe? Not quite sure there on the pronunciation. So let's take a look at what we've learned here. I'm going to switch up my color, and we'll look at some different layers here. We've got like 6 different layers. So let's imagine here the bottom layer is going to be a basalt. Now, if this is an igneous rock layer, then we can go ahead and use absolute age dating. Let's say we age this rock and we find out that it is 560 million years old. From now on, I'm just going to put MYA if it's million years old and BYA if it's billion years, just to have an abbreviation. So say on top of that basalt layer, we have a sedimentary layer. So let's say this is a sandstone. So it's a bunch of sand that solidifies and becomes sandstone. And again, this is a sedimentary layer. Well, like I said earlier, we can't use radiometric dating on sedimentary layers, so we don't know the age of that layer. If though, let's say on top of that layer, we have some feldspar. This, however, is an igneous layer. And since this is an igneous layer, we could actually age or date this layer and find out that it's 530 million years old. Now, if it's 530 million years old and this layer below is 560 million years old, then we can now start to understand through relative dating that if the sandstone is between it, it must have happened between those two time periods. Now, furthermore, let's look if there was above the feldspar, let's say there's some limestone. Limestone's actually formed from a bunch of sea creature shells being cemented together, so this is also a sedimentary rock layer, so we can't figure out the actual age of that layer. Let's say there's some shale on top of that. Well, that's also a sedimentary layer. So again, we can't use radiometric dating, but let's say on top of that we have some rhyolite. And we get rhyolite as an igneous form, so since it's magma that then crystallizes, we can now use radiometric dating, and let's say we find out that this is 510 million years old. Now, because of the law of superposition, we know that the limestone came before the shale came, otherwise the shale wouldn't be on top of the limestone. So we know that the limestone is going to be older than the shale, but we can then use relative dating to say if the feldspar is 530 and the rhyolite is 510, we can then start to come up with some ideas about when we think the limestone formed, which would be closer to 530, and when the shale formed, which would be further from 530 and closer to 510 because it's closer to that layer. So you can see how we can use this idea of having igneous rock layers and sedimentary rock layers, the law of superposition, and also relative age, combined with all of this to come up with how we can determine some ages. Now lastly, let's just pretend that we didn't know any of those ages and we then found ourselves a trilobite fossil. Or instead of doing all the radiometric dating, we might just find that trilobite fossil there in the limestone, and if we did, then we would automatically know, just because of how common that fossil is across the world, we would know that this rock layer is actually 540 to 485 million years old. Or we could get an approximate idea if we didn't have the technology or the means to be able to send in a sample of the feldspar or the rhyolite to get an actual radiometric dating. So that's where index fossils can become really handy. And there's a lot of different ones. This Paradoxidae trilobite is just one example of many index fossils. So now you see how we age and how we date different layers of the earth. Adios.